Some truths are so fundamental that once you see them, you cannot unsee them. I remember the moment I understood why light moves at exactly the speed it does, and why nothing can exceed it. Most people think of it as an arbitrary cosmic rule, like a highway speed limit posted by nature. But that's not what it is at all. The speed of light isn't a restriction placed on light. It's the speed at which causality itself propagates through space-time. It's the rate at which cause and effect can communicate. When you understand this, when you see how Einstein's equations bind energy, mass, and time into a single unified structure, you realize something profound. The universe isn't preventing us from going faster than light. The universe is telling us that faster than light is a meaningless concept, like asking what's north of the North Pole. Before we continue, take a moment to notice where you're listening from. And if this story stays with you, you're welcome to return tomorrow for what comes next. I was 23 years old when I first encountered the equations that would haunt me for the rest of my life. It was 1927, and I sat in a cramped lecture hall at the University of Göttingen, watching Max Born write symbols on a blackboard that seemed to describe reality itself. The room smelled of chalk dust and tobacco smoke. Outside, Germany was still recovering from the war, but inside that hall, we were rebuilding the universe from scratch. The speed of light had been measured precisely by then. Michelson and Morley had done their famous experiment decades earlier, showing that light moved at the same speed regardless of how you measured it. No matter which direction you pointed your instruments, no matter how fast you yourself were moving, light always traveled at 299,792,458 meters per second. Always. This troubled everyone. It made no sense. Think about it from the perspective we had then. If you're on a train moving at 50 miles per hour, and you throw a ball forward at 20 miles per hour, that ball moves at 70 miles per hour relative to someone standing on the ground. Simple addition. Galileo understood this 3 centuries before I was born, but light refused to follow this rule. If you shine a flashlight while standing still, the light moves at a certain speed. Logic says if you run forward while shining that flashlight, the light should move faster, just like the ball on the train. But it doesn't. The light moves at exactly the same speed whether you're standing still or running or flying or doing anything else. This seemed impossible. It violated everything we thought we knew about motion. I remember arguing about this with my fellow students late into the night. We would sit in beer halls, sketching diagrams on napkins, trying to find the flaw in the reasoning. There had to be a mistake somewhere. Perhaps the measurements were wrong. Perhaps there was some substance, some ether-filling space that was affecting the results. We grasped at explanations the way drowning men grasp at debris. Einstein had already published his solution in 1905, the year I was born. But understanding what Einstein wrote and truly comprehending what it meant were 2 different things. I could follow the mathematics. I could manipulate the equations. But the implications, the actual physical meaning of what those symbols represented, that took years to settle into my bones. The key was understanding what we mean by simultaneity. This sounds abstract, but it's concrete. When you say 2 events happen at the same time, what do you actually mean? You mean that if you look at a clock when one event occurs, and look at another clock when the second event occurs, both clocks show the same time. Simple enough. But here's what I didn't grasp immediately. For those clocks to be synchronized in the first place, you need to account for the time it takes for light to travel from one clock to the other. And if light always moves at the same speed, regardless of your motion, then whether 2 events are simultaneous depends on how fast you're moving when you observe them. I was working through these ideas in my small apartment one evening. I had a notebook open, filled with calculations. My landlady had complained about the lamp I kept burning past midnight, but I couldn't sleep. I was tracing through Einstein's derivation of time dilation, the phenomenon where moving clocks tick slower than stationary ones. The mathematics was clear. If you accept that light speed is constant, then time cannot be absolute. A clock moving relative to you must tick at a different rate than your own clock. Not because there's anything wrong with the clock, but because time itself flows differently for objects in relative motion. This wasn't philosophy. This was measurable, predictable, mathematical fact. I set down my pencil and stared at the wall. The wallpaper had a pattern of small blue flowers. I remember those flowers clearly because I spent a long time looking at them while I tried to absorb what I had just understood. Time was not a cosmic metronome ticking away uniformly throughout the universe. Time was flexible, relative, dependent on motion. And if time was relative, then so was space. The equations showed this with brutal clarity. If you measure the length of a moving object, you get a different answer than someone traveling alongside that object would get. Both measurements are correct. Both are real. There is no privileged reference frame, no cosmic perspective from which the true length or true time can be measured. This was disturbing. I don't mean disturbing in an exciting way. I mean, it produced a genuine sense of vertigo, of the ground falling away beneath my feet. We build our intuition about reality from everyday experience. We assume the world works the way it appears to work. And here was mathematics telling me that my intuition was wrong, that reality operated according to rules that violated common sense. But the mathematics was undeniable, and experiments were confirming it. Particles moving at high speeds in laboratories were behaving exactly as Einstein's equations predicted. They were experiencing time dilation. Their internal clocks, if you could call them that, were running slower than ours. This wasn't speculation. This was observed fact. The artifact that changed everything for me was Einstein's original 1905 manuscript. I never saw the actual document, not then, but Born had a copy of the published paper, and he would sometimes read passages aloud during his lectures. The title was On the Electrodynamics of Moving Bodies, and it was remarkable for what it didn't contain. No references to other papers, no complex mathematics. Just clear, logical reasoning, built on two simple postulates. The first postulate: the laws of physics are the same in all inertial reference frames. This means that if you're moving at constant velocity, you can't tell by doing any physics experiment whether you're moving or standing still. You need to look outside, see other objects moving past you, but within your own frame of reference, everything appears normal. The second postulate: the speed of light in vacuum is the same for all observers, regardless of their motion or the motion of the light source. This was the key. This was the postulate that forced everything else to change. From just these two simple statements, Einstein derived the entire structure of special relativity: time dilation, length contraction, the relativity of simultaneity, the equivalence of mass and energy. All of it followed, logically, inevitably, from these two postulates. I spent months working through the derivations myself, checking every step. I wanted to find an error. Part of me hoped there was a mistake, some subtle flaw that would allow reality to be simple again. But there was no mistake. The logic was airtight, and gradually, reluctantly, I accepted it. What I didn't yet understand, what wouldn't become clear until much later, was why light specifically had this special status. Why was light speed the speed that remained constant? What was so special about electromagnetic radiation that it served as the cosmic speed limit? The answer to that question would require understanding something deeper about the structure of space-time itself. Something that wouldn't fully crystallize for me until I was much older, until after the war, until after everything had changed. But in that lecture hall in Göttingen, watching Born's chalk dance across the blackboard, I took the first step toward understanding. I accepted that the universe was not obligated to match my intuition. I accepted that mathematics could reveal truths that seemed impossible, but were nonetheless real. And I began to see that the speed of light was not just a curious fact about photons. It was telling us something profound about the nature of reality itself. The constant C kept appearing in equations, not just in optics, but in mechanics, in thermodynamics, everywhere. It was woven into the fabric of physics like a recurring theme in a symphony. And slowly, I began to suspect that this was not a coincidence. This constant meant something. It was trying to tell us something fundamental about how the universe worked. But I'm getting ahead of myself. In 1927, I was just a student trying to understand equations. I didn't yet know that I would spend years of my life working on projects that would harness the energy locked inside matter, the energy described by that famous equation, E equals mc squared. I didn't know what the speed of light would come to mean to me personally, professionally, morally. All I knew then was that reality was stranger than I had imagined, and more beautiful. The universe operated according to principles that seemed bizarre, but were mathematically perfect, and I wanted to understand them completely, to see all the way to the bottom of how things worked. That desire would shape everything that came after. The disruption came in 1942, though I didn't recognize it as such at the time. I was 38 years old, and I had been asked to lead a project that would test everything I thought I understood about the relationship between matter and energy. I received a telegram on a Tuesday morning. It was brief, formal, and deliberately vague. I was to report to a location in New Mexico for work of national importance. The telegram didn't specify what kind of work. It didn't need to. By then, everyone in theoretical physics knew what was being discussed in closed meetings. what calculations were being performed behind locked doors. The artifact that arrived with that telegram was a small leather notebook, unremarkable in appearance. It contained calculations by Enrico Fermi on-chain reactions on the possibility of releasing the energy bound up inside atomic nuclei. The numbers were precise. The implications were staggering. And suddenly, the abstract equations I had spent years studying became something concrete, something that could reshape the world. I stood in my office at Berkeley, holding that notebook, and I felt the weight of it. Not the physical weight, though it was surprisingly heavy for its size. The weight of knowing that the speed of light, that constant z that appeared in Einstein's equation, was about to become more than a theoretical curiosity. It was about to become a measure of destructive power. E equals mc squared. Energy equals mass times the speed of light squared. I had taught this equation to students. I had used it in calculations, but I had never truly considered what it meant in practical terms. The speed of light is a large number. When you square it, you get an enormous number, which means that even a tiny amount of mass contains a tremendous amount of energy. A single kilogram of matter, if you could convert it entirely to energy, would release the equivalent of roughly 21 megatons of TNT. That's the energy of a large nuclear weapon, all of it locked inside 1 kilogram of material, held together by forces we were just beginning to understand. The notebook showed that you didn't need to convert all the mass. You only needed to convert a small fraction, less than 1%, and you would still release enough energy to level a city. The calculations were theoretical then, but they were based on solid physics. The nucleus of an atom is held together by powerful forces. If you could split certain heavy nuclei, they would break into lighter pieces, and those pieces would weigh slightly less than the original nucleus. That missing mass would appear as energy, traveling outward at the speed of light. I took the train to New Mexico 3 weeks later. The landscape was stark, beautiful, in a desolate way. Red rock and empty sky. I had brought books with me, technical papers, but I spent most of the journey looking out the window, thinking about what I was being asked to do. The project site was isolated, built quickly, utilitarian. There were laboratories, machine shops, housing for the scientists and technicians who would work there. Everything was designed for one purpose, to build a device that would demonstrate the practical application of Einstein's equation. I met with other physicists who had been recruited. Hans Bethe, Richard Feynman, Niels Bohr, men I had admired, whose papers I had read, whose lectures I had attended. We sat in a conference room and we discussed the technical challenges. How to obtain the necessary materials. How to configure them to sustain a chain reaction. How to trigger the reaction at the right moment. The physics was straightforward in principle. Uranium-235 or plutonium-239, when struck by a neutron, would split and release more neutrons. Those neutrons would strike other nuclei, causing them to split as well. If you arranged the material correctly, with enough of it in a small enough space, the reaction would accelerate, feeding on itself. In a fraction of a second, an enormous amount of energy would be released. The energy would appear as heat, as light, as the kinetic energy of the fragments flying apart. And all of it would happen at speeds approaching the speed of light itself. The neutrons would travel fast. The gamma rays would travel at exactly the speed of light. The shock wave would move more slowly, but the initial energy release would be nearly instantaneous from any human perspective. What struck me during those early meetings was how the speed of light kept appearing in our calculations, not just as a constant in Einstein's equation, but as a fundamental limit on how quickly information could propagate. When a neutron splits a nucleus, the fragments fly apart at a certain speed. If they're moving too fast, they'll escape the mass of material before they can cause more fissions. The timing had to be precise. We needed the material to be compressed, held together long enough for the chain reaction to propagate through the entire mass. And that meant understanding not just nuclear physics, but the physics of shock waves, of materials under extreme pressure and temperature. We needed to calculate how fast the reaction would spread, how quickly the energy would escape, how to maximize the efficiency of the process. I spent my evenings walking through the desert. The stars were bright there, away from city lights. I would look up at those stars and think about the light traveling from them, crossing vast distances at that same constant speed. Some of those stars were so far away that their light had been traveling for millions of years before reaching my eyes, and yet it still moved at the same speed, that unchanging c. The work consumed us. We set up experiments to measure the properties of materials under conditions that had never been studied before. We built equipment, refined our calculations, argued over designs. There was a strange excitement to it, the thrill of doing something new, something that required every bit of our understanding of physics. But there was also an undercurrent of unease. We all knew what we were building. We told ourselves it was necessary, that the war required it, that the other side was pursuing the same goal. These things were true, but they didn't eliminate the discomfort of knowing that we were creating something designed to kill as many people as possible in the shortest amount of time. I tried not to think about that part. I focused on the physics, on the technical challenges. There was a purity to the work, a kind of intellectual satisfaction in solving difficult problems. When you're deriving equations, checking calculations, running experiments, you can lose yourself in the details. The broader context fades into the background. One night, I was reviewing Fermi's calculations on neutron multiplication. The notebook I had been given was open on my desk, and I was working through the mathematics step by step. The chain reaction required a delicate balance. Too little material, and the neutrons would escape before causing enough fissions. Too much material in the wrong configuration, and it would react prematurely. We called the minimum amount of material needed to sustain a reaction the critical mass. Below critical mass, nothing happens. At critical mass, the reaction is just barely self-sustaining. Above critical mass, the reaction accelerates rapidly. The difference between a fizzle and a functional weapon was a matter of precise engineering. As I worked through the numbers, I realized something that should have been obvious from the start. The speed of light wasn't just relevant because of E equals mc squared. It was relevant because it set the timescale for everything that happened. The reaction would occur on a timescale measured in microseconds, millionths of a second. In that time, light would travel only a few hundred meters. The entire device would be smaller than that, which meant that nothing, no signal, no information could travel across the device faster than light could. The reaction would propagate at a speed limited by how fast neutrons could travel, which was much slower than light, but the energy released would move outward as gamma rays and heat at the speed of light. And once that energy started moving, there was no stopping it, no way to recall it or contain it. We were building a device that would convert matter to energy according to a precise equation, and that energy would then propagate according to the same laws that governed everything else in the universe. The speed of light would determine how quickly the destruction spread, how far the heat and radiation would reach, how fast the shock wave would form. I closed the notebook and sat in the darkness of my office. Outside, the desert was silent. Inside, I could hear my own breathing. And I understood that I was no longer just studying the speed of light as an abstract constant. I was preparing to use it as a weapon. The first test was scheduled for July 1945. We called it Trinity, though I never learned who chose that name or why. By then, we had been working for 3 years, and the device was ready. All the calculations have been checked and rechecked. The materials have been assembled. The timing mechanisms had been tested. Everything was as prepared as we could make it. I slept poorly the night before the test. Not from excitement, though there was some of that. Mostly from a growing sense that we were about to cross a threshold that could not be uncrossed. Once we demonstrated that this was possible, once we showed that human beings could release this much energy in such a short time, the world would be different. There would be no going back to the world where this was merely theoretical. The test site was in the Jornada del Muerto desert, the journey of the dead man. I thought about that name as we drove out to the observation point in the pre-dawn darkness. The device sat on a tower about 100 feet tall, surrounded by instruments that would measure the blast, the temperature, the radiation. We would be watching from a distance of several miles. The artifact that I carried with me that morning was a piece of welding glass, dark enough to protect my eyes from the flash. We had been told to lie face down on the ground when the device detonated, to not look directly at it, but I knew I would look. I had spent 3 years working toward this moment. I needed to see it. We waited in the bunker as the countdown proceeded. The radio crackled with status updates. The sky was still dark, but there was a hint of dawn on the horizon. Someone had brought coffee. It tasted bitter. Or perhaps that was just my mood. I held the welding glass in my hand and thought about what was about to happen. In a few minutes, a carefully arranged mass of plutonium would be compressed by conventional explosives. The compression would bring it above critical mass. Neutrons would begin splitting nuclei. The reaction would cascade, doubling and redoubling in less than a microsecond. In that fraction of a second, a significant portion of the plutonium would undergo fission, and
The energy binding its nuclei together would be converted to heat and radiation, according to Einstein's equation.
The speed of light would govern every aspect of what happened next. The gamma rays would leave the center of the reaction at exactly 299,792,458 meters per second. They would reach the outer edge of the device before the material had time to fly apart. They would heat the air around the device to temperatures comparable to the surface of the sun. That heated air would emit visible light, also traveling at the speed of light, creating a flash that would be seen for 100 miles. Then the shock wave would form, traveling much slower, at the speed of sound in the superheated air. It would arrive at our bunker several seconds after the flash, carrying energy that could shatter windows and knock down buildings. But by then, the initial reaction would be over. The energy would have been released. The matter would have been converted. The speed of light would have determined how quickly it all happened. The countdown reached 10 seconds. I put on the welding glass and looked toward the tower. The sky was getting lighter now. I could see the outline of the mountains in the distance. Everything seemed very still, very quiet. Zero. For a moment, nothing happened. Then the world turned white. I had expected brightness, but this was beyond brightness. This was light of an intensity I had never imagined. Even through the dark glass, even with my eyes partially shielded, the flash was overwhelming. It seemed to fill the entire sky, to eliminate shadows, to render everything in stark, absolute illumination. The light came first because light travels at the speed of light. The information that the reaction had occurred, transmitted by photons, reached my eyes in a tiny fraction of a second. My brain registered the flash before the device had even finished its work, before the fireball had fully formed, before any sound had reached us. I lowered the glass and looked directly at what we had created. A ball of fire was rising from the ground, expanding rapidly, churning with internal motion. It was orange and red and yellow, colors of heat, of matter at temperatures that should not exist outside the sun. The ball rose, climbing into the sky, pulling dust and debris up with it, forming a column beneath it. The mushroom cloud. We hadn't predicted that specific shape, though some of the calculations had suggested something like it might form. The heated air rising rapidly, the cooler air rushing in to replace it, the dynamics of the explosion creating that distinctive form. It was beautiful in a terrible way. Then the sound arrived. Not a single sound, but a rolling, sustained roar that seemed to come from everywhere at once. The bunker shook. I felt the shock wave pass through my body, a physical pressure that made my chest tight. And still the fireball continued to rise, continued to expand, glowing against the dawn sky. I turned away and sat down on the concrete floor of the bunker. My hands were shaking. Someone was speaking, saying something about the measurements, about the yield, about how successful the test had been. The words seemed to come from very far away. What I had just witnessed was the conversion of matter to energy at a rate and scale that had never occurred on Earth before. In less than a second, we had released more energy than the largest conventional bomb could release. And we had done it using the equation that related mass to energy through the speed of light. The equation was elegant, simple. E equals mc squared. 3 symbols. But those 3 symbols described a process of such violence, such raw power, that seeing it made me question everything I had thought about the beauty of physics. The equation was still beautiful. The mathematics was still elegant. But the application was horrifying. Bessa found me sitting there and asked if I was all right. I told him I was fine, though I wasn't sure that was true. He said the device had worked better than we had hoped, that the yield was higher than predicted. This was good news, he said. It meant our calculations were correct. It meant the weapon would be effective. I nodded but didn't respond. What could I say? That I was disturbed by our success? That I wished the test had failed? That would have been a lie. Part of me was proud of what we had accomplished. We had taken theoretical physics and made it real. We had shown that human beings could manipulate the forces that powered the sun. But another part of me, a part I had been suppressing for months, was screaming that we had made a terrible mistake. We had given human beings the power to destroy cities, to kill hundreds of thousands of people in seconds, and we had done it during a war, which meant the power would be used. There was no question of whether, only of when and where. The speed of light had enabled this. Not morally, not causally, but physically. The relationship between mass and energy, mediated by that constant, had made it possible to extract this much power from matter. And because light speed was so large, because squaring it produced such an enormous number, even a small amount of matter could release devastating energy. I thought about my time in Göttingen 17 years earlier.
when I had first wrestled with the implications of special relativity.
Then, the strange consequences of constant light speed had seemed purely theoretical, divorced from practical concerns. Time dilation, length contraction, the relativity of simultaneity, these were fascinating puzzles, but not things that would affect ordinary life.
Now I understood how naive that view had been. The speed of light wasn't just a theoretical constant. It was woven into the fabric of how the universe worked. It determined how fast causality could propagate.
It connected mass and energy in a fundamental way. And because of that connection, it had given us the power to destroy ourselves. Over the following weeks, we refined the design based on what the test had shown us. The measurements confirmed our calculations, but also revealed areas for improvement. We could make the device more efficient, more powerful, more reliable. The physics was now proven. The engineering could be optimized. I participated in these discussions, offered my suggestions, reviewed the modified calculations. But something had changed in me. I went through the motions, did the work, but I felt disconnected from it. At night, I would lie awake and see that flash again, that moment when the world turned white. The device we had built released its energy in less than a microsecond. In that time, light travels about 300 meters.
The entire reaction occurred within a space smaller than that, governed by the speed at which information could move. The neutrons traveled at a fraction of light speed, perhaps 10,000 kilometers per second. The gamma rays traveled at light speed, and the energy, once released, propagated outward according to the same physical laws that govern stars and galaxies. There was no malice in the physics. The equations didn't care what we used them for. E equals mc squared was true whether we were calculating the energy output of the sun or the yield of a weapon. The speed of light was constant, whether it was carrying starlight to our eyes or carrying the heat of an explosion outward from ground zero. But I cared. I was beginning to understand that knowledge alone was not enough, that understanding the universe did not absolve us of responsibility for what we did with that understanding. The speed of light was a fundamental constant, yes, but we had chosen to use it in this particular way. In August, we received word that the weapon had been used, not once but twice. 2 cities, hundreds of thousands of people dead or dying. The war would end soon, they told us.
The device had worked as intended. Our calculations had been proven correct under real-world conditions. I should have felt vindicated. The physics had been right. The engineering had been successful. We had accomplished what we set out to do. But all I felt was a deep, heavy sadness that I carried with me like a weight I could not set down. Years later, I would quote the Bhagavad Gita, "Now I am become death, the destroyer of worlds." People would remember that quote, associate it with me, with that moment. But what I actually felt was simpler and more personal. I felt that I had helped create something that could not be uncreated, and that the world would be shaped by it forever after. The speed of light had not changed. It was still the same constant it had always been. But my understanding of what it meant had changed completely. It was 1,952 when I finally understood what the speed of light really meant. Not as a number, not as a constant in an equation, but as a fundamental feature of reality that determined what was possible and what was not. I was no longer at Los Alamos. The war had ended 7 years earlier. I had returned to teaching, to research, though my reputation was forever tied to the weapon. People would introduce me at conferences and mention my role in the project, as if that were the sum of my contributions to physics. It bothered me, but I understood it. What we had done was significant enough to overshadow everything else. I was working on a different problem then, trying to understand the structure of space-time itself. Einstein had shown that gravity was not a force in the traditional sense, but a curvature of space-time caused by mass and energy. This was his general theory of relativity, published in 1915, and it was even more radical than special relativity. The artifact that changed my understanding was a set of lecture notes from a seminar series at Princeton. The speaker was discussing the geometric nature of space-time, and he had drawn diagrams showing how light cones define the causal structure of the universe. I had seen these diagrams before, but this time something clicked. I saw what they were really showing me. Imagine you were at a point in space and time. Call this point here and now. From this point, you can influence the future by sending signals or objects outward. But you cannot send those signals faster than light, which means that the region of space-time you can influence is limited by how far light can travel in a given time. If you draw this on a diagram, with space on the horizontal axis and time on the vertical axis, the boundary of the region you can influence forms a cone shape. This is called your future light cone. Everything inside the cone can be causally connected to you. Everything outside the cone cannot be reached by any signal you send, because doing so would require faster-than-light travel. Similarly, the past light cone represents all the events that could have influenced you, all the points in space-time from which a signal could have reached your current location. Again, this is limited by the speed of light. Events outside your past light cone are causally disconnected from you. They might as well not exist as far as your present moment is concerned. This geometric structure, this division of space-time into regions that can and cannot be causally connected, is fundamental. It is not something imposed by human limitations or technological constraints. It is built into the structure of reality itself. And suddenly I understood what the speed of light actually was. It was not primarily about light. Light just happened to travel at this speed because photons have no mass. But the speed itself, that constant c, was the speed at which causality propagates through space-time. It was the maximum rate at which cause and effect could be linked. I sat in my office with those lecture notes spread before me, and I felt the same vertigo I'd experienced as a student in Göttingen, that sense of the ground shifting beneath me. But this time, it was different. This time I was not learning that reality violated my intuition. I was learning why it had to be this way. If there were no speed limit on causality, if cause and effect could propagate instantly across any distance, then the concept of now would be absolute. There would be a universal present moment, the same for all observers regardless of their motion. But we know from experiment that this is not the case. Moving clocks tick at different rates. Simultaneity is relative. Different observers disagree about which events happen at the same time. The only way to reconcile these observations is if causality itself has a finite propagation speed. And that speed, that maximum rate at which information can travel, is what we call the speed of light. It is not arbitrary. It is not merely a property of electromagnetic radiation. It is a fundamental feature of space-time geometry. This meant that when Einstein wrote E equals mc squared, he was not just relating energy to mass. He was revealing something about the structure of reality. The speed of light squared, that enormous number, was not just a conversion factor. It was telling us that mass and energy are two forms of the same underlying thing, and that the rate at which this thing manifests in different forms is governed by the fundamental speed limit of causality. I thought back to the Trinity test, to that moment when matter was converted to energy. What I had witnessed was not just a powerful explosion. It was a demonstration that the separation between mass and energy is not absolute, that they are interchangeable, and that the rate of exchange is set by the geometry of space-time itself. The weapon worked because of this geometry. The energy was released at a rate determined by how fast neutrons could travel through the material, which was much slower than light. But once the energy was released, it propagated at the fundamental speed limit. The gamma rays left the center of the reaction at light speed. The heat, the radiation, the destruction, all of it spread according to the same geometric constraints that governed everything else in the universe. I began working through the mathematical implications of this understanding. If space-time has a fundamental structure that limits the speed of causality, then certain things become impossible, not just practically, but logically. You cannot send a signal faster than light, because faster than light is equivalent to traveling backward in time from some reference frames. This was not immediately obvious, but the mathematics was clear. If you could move faster than light, you could construct scenarios where an effect preceded its cause, where you could send a message to your own past. This would create paradoxes, contradictions in the causal structure of space-time. The universe avoids these paradoxes by making faster-than-light travel impossible. The speed limit is not a law in the sense that speed limits on highways are laws, rules that can be broken if you are willing to pay the penalty. The speed of light is a limit in the sense that it defines what speed means in the first place. It is built into the metric structure of space-time, into the way distances and durations are related to each other. I had spent years thinking about the speed of light as a curious constant, a number that appeared in equations and had to be measured carefully. Now I understood that it was much more fundamental than that. It was the conversion factor between space and time, the rate at which one dimension of space-time could be traded for another. When you move through space, you move through time more slowly. When you sit still in space, you move through time at the maximum rate. This is time dilation, but understood geometrically rather than as a mysterious effect. You are always moving through space-time at the speed of light, but that motion is divided between motion through space and motion through time. The faster you move through space, the slower you move through time, such that your total speed through space-time remains constant. This was why nothing with mass could reach the speed of light. To do so would require all of your motion through space-time to be directed through space, leaving none for time. You would experience no passage of time. From your perspective, you would arrive at your destination at the same instant you departed, regardless of the distance. Time would not exist for you. Photons, having no mass, travel at exactly this speed. They move through space at the speed of light and do not move through time at all.
A photon, emitted by a distant star, experiences no passage of time during its journey to Earth. From the photon's perspective, if it could be said to have a perspective, emission and absorption are the same event.
I wrote these ideas down, developed the mathematics, checked my reasoning. The understanding felt solid, grounded in the geometry of space-time rather than in arbitrary rules. The speed of light was not a speed limit imposed on objects. It was the natural consequence of how space-time was structured, of how cause and effect were connected. This realization changed how I thought about the weapon. The energy released in an atomic explosion was not just a large amount of energy. It was matter, transforming into other forms, with the rate of transformation determined by the fundamental geometry of reality. We had not violated any laws of physics. We had not discovered some loophole or exploit. We had simply arranged matter in a configuration that allowed this transformation to occur rapidly. The moral weight of that remained unchanged. Understanding the physics more deeply did not absolve us of responsibility. If anything, it deepened the weight. We had used our knowledge of fundamental reality to create a device for killing. The beauty of the underlying physics did not make the application beautiful, but it did help me understand why the speed of light appeared everywhere in our calculations. It was not just a coincidental constant. It was the fundamental rate at which reality operated, the speed at which causality propagated, the conversion factor between mass and energy, the limit on how fast information could travel. All of these were different aspects of the same underlying geometric truth. I gave a lecture on these ideas at a conference in 1953. The room was full of physicists, many of whom had worked on similar problems. I explained the geometric interpretation of light speed, the way it defined the causal structure of space-time, the impossibility of faster-than-light travel, not as a technical limitation, but as a logical consequence of how reality was organized. After the lecture, a young physicist asked me a question. If the speed of light is truly a fundamental limit, if nothing can exceed it, then doesn't that mean the universe is constrained in certain ways? Doesn't it mean that some things we might imagine are simply impossible? I told him yes. The universe is constrained. Causality cannot propagate instantly. Information cannot travel faster than light. Energy cannot be created or destroyed, only transformed. These constraints are real and absolute, but they are not arbitrary restrictions. They are consequences of the underlying structure of space-time. The constraints create possibilities as well as limitations. Without the finite speed of causality, without the relative nature of simultaneity, without the connection between mass and energy, the universe would be fundamentally different. Stars might not shine. Atoms might not be stable. The very existence of matter as we know it depends on these constraints. I thought about this often in the years that followed. The speed of light was a limit, yes. But it was also the speed at which light traveled, at which causality connected events, at which the universe evolved and unfolded. It was not a wall preventing us from doing something. It was the rate at which reality operated. When I looked at the equation E equals mc squared now, I saw it differently than I had as a young student. I saw it not as a formula for converting mass to energy, though it was that. I saw it as a statement about the geometry of space-time, about how the fabric of reality allowed matter and energy to be different manifestations of the same underlying thing. The speed of light was the constant of proportionality, the number that converted between mass and energy. It was large because space-time was structured in a particular way, because the rate of causal propagation was what it was. In a universe with different geometry, this constant might be different. But in our universe, In the reality we inhabited, it was 299,792,458 meters per second. Always, everywhere, without exception. This was what I had uncovered, though uncovered might be the wrong word. Einstein had already shown all of this. What I had done was internalize it, make it part of how I understood the world. The speed of light was not just a fact to be memorized, or a constant to plug into equations. It was the fundamental speed of reality, the rate at which cause and effect were connected, the maximum speed at which anything could influence anything else. And once I understood this, I could never see it any other way. I am 78 years old now. The year is 1963. And I sit in my study looking at papers that span 40 years of thinking about the speed of light. The equations have not changed. The constant c is still the same value it was when I was a student. But my relationship to that constant has been transformed by decades of work, understanding, and regret. The artifact on my desk today is a photograph from the Trinity test. Someone took it in the moments after the explosion, showing the mushroom cloud rising into the dawn sky. I keep it not as a trophy, but as a reminder of what happens when theoretical physics becomes applied engineering, when understanding the universe leads to the power to reshape it. Young physicists sometimes visit me, asking about those years, about what it was like to work on the project. They want to know about the technical challenges, the calculations, the moment of the test. I answer their questions, but I also tell them what they usually do not want to hear, that understanding how the universe works does not tell you what to do with that understanding. The speed of light is a fundamental constant. It governs how causality propagates, how mass and energy are related, how space-time is structured. These are facts, as true now as they were in 1905 when Einstein first wrote them down, as true as they will be 1,000 years from now. The physics does not change based on our wishes or our moral reasoning, but what we do with that physics, that changes constantly. We chose to build weapons. We could have chosen differently, though perhaps not given the circumstances of war, the pressure of competition, the fear of what would happen if we did not build them first. I do not know if we made the right choice. I suspect there was no right choice, only a series of decisions that seemed necessary at the time. What I do know is this. The speed of light showed us that mass and energy are interchangeable, and we used that knowledge to release energy from matter in the most violent way possible. The same knowledge that let us understand stars, that explained where the sun's power comes from, that revealed the deep structure of reality, also gave us the ability to destroy cities. This is not a paradox. It is simply a fact about knowledge. Understanding the universe gives you power, and power can be used for any purpose. The equations do not care. E equals mc squared does not distinguish between the fusion reactions in the sun and the fission reactions in a bomb. The speed of light does not judge. But I care. I have spent years thinking about what we did, about whether it was justified, about what responsibility we bear for the consequences. The weapons we built were used. Cities were destroyed. Hundreds of thousands died. The war ended, yes. Perhaps lives were saved in aggregate. These are the arguments people make, and they may be true. What is also true is that we unleashed something that cannot be contained now. Other nations have built their own weapons. The calculations are not secret anymore. The physics is understood. Any country with sufficient resources and determination can build a device that converts matter to energy according to Einstein's equation. The knowledge has spread, and it will continue to spread, because knowledge is not something that can be put back once it is released. I think sometimes about that young student I was in Göttingen, working through the equations of special relativity, marveling at how strange the universe was. I was not thinking then about weapons or destruction. I was thinking about understanding, about seeing deeper into how things worked, that curiosity was pure, or as pure as anything human can be. The curiosity led to knowledge. The knowledge led to power. The power was used in ways I did not fully anticipate, though perhaps I should have. This is the trajectory of physics in the 20th century, compressed into a single life. Discovery, understanding, application, consequence. The speed of light remains what it always was. It is still the fundamental speed of causality, still the conversion factor between mass and energy, still the limiting velocity that shapes the structure of space-time. None of that has changed. What has changed is that we have learned to manipulate the processes governed by that constant, to arrange matter in configurations that release energy rapidly, to build devices that kill on scales that would have been unimaginable a century ago. I teach occasionally now, though not as often as I once did. When I talk to students about relativity, about the speed of light, about E equals mc squared, I try to convey not just the mathematics, but the weight of understanding. These are not just formulas to memorize. They are descriptions of how reality works, and understanding them gives you power.
What you do with that power is not determined by the physics. The equations will work whether you use them to build power plants or bombs, to understand stars or destroy cities.
The moral choices are separate from the scientific understanding, though they are informed by it. Some people have told me that I should not feel responsible, that I was simply doing physics, that the decisions to use the weapons were made by others. This is technically true. I did not order the bombs dropped. I did not choose the targets. But I did the calculations. I solved the problems. I helped make it possible. That responsibility cannot be evaded with technicalities. Other people have told me that I should feel proud, that the work shortened the war, that it saved lives in the long run. This may also be true. I do not know. I was not privy to all the strategic calculations, all the estimates of casualties that would have resulted from other courses of action. Perhaps the weapons were necessary. Perhaps they were not. History will judge that better than I can. What I can judge is the physics. And the physics is beautiful, even when its applications are terrible. The speed of light as the fundamental limit on causality, as the speed at which reality operates, as the conversion factor between mass and energy, this is profound and elegant. It reveals something deep about the structure of the universe. That beauty does not excuse what we built, but neither does the application negate the beauty. These are separate things, and it is important to me that they remain separate in my mind. The physics is true and beautiful. The weapon is powerful and terrible. Both statements are correct. I look at the photograph on my desk, at that cloud rising into the sky, and I remember that moment when light speed stopped being an abstract constant and became something concrete, something that determined how quickly energy could propagate, how far destruction could reach, how fast the world could change. The speed of light has not changed. It is still 299,792,458 meters per second. It will always be that value in this universe, according to this geometry of space-time. What has changed is that I understand it now, not as a student learning physics, but as a man who helped demonstrate what that constant means in practical terms. I understand why nothing can exceed the speed of light. It is not a rule that can be broken with sufficient technology or cleverness. It is a fundamental feature of how space-time is structured, how cause and effect are connected, how reality operates. The light cone defines what is possible. Everything inside the cone can be reached. Everything outside cannot be, not without violating causality itself. This limit is absolute. But within the limit, within the boundaries set by the geometry of space-time, there is enormous scope for action, for discovery, for both creation and destruction. The speed of light does not prevent us from splitting atoms or fusing them, from releasing energy or harnessing it, from understanding the universe or reshaping it. It only sets the rate at which these things can occur, the speed at which information can propagate, the fundamental tempo of reality. And that, I've learned over a lifetime of working with these equations, is both a constraint and a gift. The universe operates at a certain speed. We can work within that speed, but we cannot exceed it. I am old now. I have perhaps a few years left, perhaps less. The speed of light will outlast me by an eternity. It will govern the universe long after every person who worked on the project is gone, long after the weapons have been dismantled or used, long after this particular moment in history has faded into the past. That constant, that unchanging value connects everything. It connects the light from distant stars to my eyes. It connects mass to energy. It connects cause to effect. It connects the physics I learned as a young man to the weapons we built, the understanding to the application, the beauty to the terror. And it remains, as it has always been, the fundamental speed at which reality unfolds.